Howdy. The purpose of this video is to talk about ionic structures and how we describe them. Now, we've already talked about metallic structures, which are composed of hard spheres that are closely packed. Ionic structures are very similar. Again, we're thinking about these things as individual ions being hard spheres. However, now we have an added degree of complexion, and that's because these spheres can either be positively charged or negatively charged. So here's one example. This is a material called lead zirconium titanate. It's composed of lead, titanium zirconium, and oxygen. And this is an important material because it has a very large piezoelectric effect, so change in the voltage if I compress it in one direction. But in order to be able to talk about this and describe this, and even more importantly, understand why these atoms are arranged in this specific arrangement, we need to be able to understand ionic structures. Okay, so again, we talked about ionic materials having at least two different kinds of particles. So there are anions, negatively charged ions, and we have cations, positively charged ions. Now, typically, anions are going to be larger than cations because they have extra electrons, but that's not always the case. So there's an attractive force between oppositely charged particles, but there's a repulsive force between similarly charged particles, right? Two anions don't want to get too close together. There's a repulsive force between them, pushing them apart. So really, ionic structures assemble in such a way to maximize those attractive forces and to minimize the repulsive forces. So we're going to work through an example, and this is sodium chloride. So this is common table salt. I've shown you the particular structure for sodium chloride, but what we want to ask is how did we get to this particular structure? And we got there by answering two questions. The first question is, which sites? So what I mean is ionic materials, we typically think of them as having an anionic lattice, so a lattice of anions, and cations are sitting in particular locations in that anionic lattice. So which locations are they sitting in? And that comes down to the relative size of the two different materials. So the second point then is how many. So how many of those sites are occupied? This ultimately comes down to the stoichiometry, how many anions per cation, and how many available sites are there in a particular lattice. So let's keep working through this example. The first question I said, which sites? Now there's a rule, and that rule is that cations will occupy the largest available site that is less than or equal to their size. So let's think about that with a picture first, and then we'll come back to the words. So if I picture 4 anions here, so these are negatively charged, if the cation is smaller than the available site, so the site is out here, the cation is smaller than that. That's an unstable configuration. It's unstable because we have this repulsive force, right? Those anions want to spread away from each other. They're being repelled from each other. So if we have a very small cation, this is an unstable configuration. On the other end, if we have a cation that's a little bit bigger than those anions, then it pushes all the anions out a little bit. And remember, the anion to cation interaction is attractive. And so this is a more stable configuration, right? There's an attractive energy between that cation and that anion, and the neighboring anions are being pushed apart from each other a little bit. So this is a stable configuration. The limit would be when it's exactly the right size. And so we say that this is a stable configuration as well, although it's very, very rare to find a radius that's exactly the same size as that potential hole. But this is only true to some limit, right? So as this cation gets larger and larger, at some point, now we're not going to have a stable configuration anymore because the cations will be impinging on other cations. And so we come back to the rule that cations want to occupy the largest available site that is a little bit smaller than they are. So let's think about this in terms of sodium chloride. And we can think about this in terms of the radius ratio of the cation to the anion. And we can do this because we know that if we have an anion lattice, so for example, if we have an FCC lattice, the available size of the different sites, so for example, there's an octahedral site right in the middle of the FCC lattice, the available size of that lattice, I can calculate out the size of that interstitial position as a function of the anion radius. And so if I look at the cation to anion ratio, I can basically look at a table and say what kind of a site those cations will like to occupy. So for this case, sodium plus is 116 picometer, that's the radius, and chlorine anion is 167 picometers. So if I look at that ratio, the cation over the anion, I get a value of 0.695. And we can see that that falls within the range that's acceptable for an octahedral hole. And so what that means is that that cation, sodium, is a little bit bigger than the size of the octahedral hole, but it's a little bit smaller than the next available site. So the next one would be a cubic available site, and that the size of that available site is 0.732 times the radius of the anion. So again, we found the radius ratio, cation over anion. We looked at our table, and we say that in the sodium chloride lattice, sodium wants to occupy octahedral sites. So it's going to sit in octahedral sites such as this one. But the next question is, how many of those sites is it going to occupy, right? So for example, we could occupy half of the sites. Remember, in an FCC lattice, we have 4 octahedral sites. So this is one full site because it's entirely within it. This one is 1/4 of a site because only 1/4 of that sphere is within the unit cell. But if I look at all of these 4 together, that adds up to 1. So these are 2 available sites. That's half of the sites. So that's one potential configuration. Or we could think about maybe it's occupying all the sites. So how do we figure this out? And that comes down to the stoichiometry of the solid. So we know that we need 1 sodium for each 1 chlorine that we have, right? So let's look at the FCC lattice again. In 1 unit cell, we have 4 atoms of 4 atoms of chlorine. These are actually ions, right? So 4 chlorine ions. And so essentially we need to occupy 4 octahedral sites with sodium. And that'll give us a 1-to-1 ratio of sodium to chlorine. And that is the case if all of the octahedral sites are occupied. Okay, so we've thought about ionic structures. We've talked about how they also follow a close-packed hard sphere model. But the 2 important things, right? Ionic radius ratios are going to tell you which sites are occupied. Are those cations sitting in cubic sites, octahedral sites, tetrahedral sites? Certain lattices do or do not have certain sites. So for example, the BCC lattice does not have tetrahedral sites. So if you found by the ionic radius ratio that the cations want to sit in tetrahedral sites, then those anions are not going to be coordinated in a BCC structure. And finally, we talked about stoichiometry, how many of the sites are occupied. And so in the FCC case, for sodium chloride, we know there's a 1-to-1 ratio. And so that meant that all of those octahedral sites had to be occupied.